messed up.
No, I didn't. You did.
No, you messed up.
No, your parents did.
Let me see it.
Oh, okay. Well, I guess that's...
Why? What? He does not need to be drawn like this.
He does, because I was paid.
Because you were paid? Oh.
Yeah, I was paid. Oh, that shit. Maybe just stop. Maybe. Yeah, that's a good idea. I agree.
Why?
Oh shit, it's Pat.
I've already seen all of this.
I forgot about Pat. Why are you dead?
Why am I what?
No, that's...
Are you talking to Pat?
No.
I didn't say anything about it.
Thinking?
No, I wasn't. You can't assume that I was thinking about something.
You're right, I can never think that. I assume that you're thinking. Stop, you're gonna break it. These are Buddhist prayer beads.
Why? What?
My family is Buddhist. No. Oh, it's tiny Chris Burrows.
I think I will go ahead and give
No tests?
A thing? A thing?
sorry, I have not gotten much sleep recently.
Even.
Yes.
We all know you have him.
To give you a makeup
What?
thing. You know, like I did last time. I think I'll give you
These beats are fun.
so, the test
I enjoy these beats.
better than last time.
You can try it.
I've had them for years. I know.
Just wiggle them around. They're like snakes running through your hands.
Both.
Okay, fine. Yeah. The average for this class is a 69.7. Overall is a 71.
Dr. Bob, what's that standard deviation?
Standard deviation is 10. Let's say this class is 11.9.
Watch me be.
Wow, you guys like make a big deal out of this. It's like it's different by 2. It's not actually a big deal.
That is a big deal.
No,
That is a big deal.
because you only get one. You get one grade out of standard deviation. You guys want to use statistics with reality.
You're right. Reality is a lot worse.
Of course it is.
If we don't get the grade, it will become
Anyway,
stable.
I want to be dead.
a good chunk of the test actually went totally fine, but there are other parts that did not go super fine. And so that's why some of the scores are a bit lower.
Fine.
So like I said, I think I'll go ahead and do a follow-up question similar to last time. The time scale is shorter, obviously it has to be, right? But the question is easier, so I think it should be fine. It's harder to make these things really hard, you know, compared to the relativity problems. So anyway, I'll start by handing these out. So this score is, of course, the raw score before we
Why do I go first?
I want to be not alive.
Told you I was the bottom.
Oh damn, it's pretty good actually.
No, it's not.
Yes, it is.
Look at Benji's.
What do you get?
64.
God damn it, Benji.
You like my statistics?
Oh, I did really poorly in
I would have done that at a 9, but I figured he would have like been a little bit. I didn't even get any of these right.
I got one slightly less.
Flipping 7.
You did better on me in C and D.
Wow.
I bet I died in the last.
Show me your Feynman diagram.
Oh, I didn't do that bad.
Oh, my Feynman diagrams are wrecked.
Same
That's
here.
not the Feynman diagram page. What?
Rip.
We got...
It's impossible. It breaks the conservation of energy.
And baryon number.
I said Varian.
If we had Micah, if we had combined our answers.
Wait.
Then it wouldn't have done anything.
But I said Varian.
Where?
Yeah, but you also diagrammed it out.
Yeah, I diagrammed it out before being like, wait a second, that's fucking stupid.
Why didn't you erase the diagram?
I don't know, I was rushing.
I enjoy this real good.
Wait, how is this wrong?
Because you have to like say it with the short. Oh, because I don't know. RGBR. It's not wrong. It's the same thing I put.
How about we go over the... Do it.
I'd rather not.
I want to be dead.
I can arrange that.
Micah, I wasn't sure if I should put Micah. If I had put these, I would have gotten C. So what do we do?
I was kind of surprised on. It should have been easy. But I guess, I don't know, I think maybe the lack of specifics, like not saying draw this time diagram exactly like this, which I thought would make things easier. I think they made things harder because we weren't used to that or something. So you can actually start with whatever you want, and you can do it with any pi. Let's say you go pi plus is probably easiest. An easy way to do this is to annihilate it to a W plus.
Am I still guessing?
Which then goes to a muon neutrino and an anti-muon. But I told you to make an anti-muon, so here's an anti-muon. It's easy to do if you start with pi plus. You actually can do it with the pi minus just as well or pi naught just as well. You just have to have a few things left over, which is no big deal. Like for example, you could do it with a pi naught going U bar annihilating to a photon that goes to mu minus mu plus. That's also an anti-muon, right? So that will work as well. Anyway, so that's only, it's not the only way to do it. Then they have an anti-muon. Then I said that anti-muon has to decay to a muon anti-neutrino plus other stuff. So the easy way to do that is have the anti-muon emit a W. So that this now becomes a muon anti-neutrino. The W can be to anything you want as long as it's stable. So I would say something like a positron and a neutrino would be the easiest way to do it. Some people just had, I think, trouble figuring out I don't know what I meant or what was expected, but it should be, it has to go to an anti-muon, that's going to be an anti-neutrino, and then all the other particles that exist should be stable particles. So that was the other thing. If you ended with just free quarks, or if they ended with something unstable, like a ion or something, it's an unstable particle, or a muon. Muon. Oh, muon, or, well, yeah, right. The stable particles would be like electrons or photons or something like that, right? That would be the issue. Anyway, if you did that, it was only some of the points, and that's how it works. So anyway, this is the basic diagram I was looking for. For part B. Okay, so part B really requires you to have read the question. Yes. You have to make sure you understand what it's talking about. The main thing is all there. It says that the states of mass and flavor do not commute. And to make it easy to make it easier for you, I'm not saying it's easy, to make it easier for you, I made it clear that the muon neutrino is in a mass eigenstate. That is to say, so if you have flavor eigenstates and you have mass eigenstates, and you know that you cannot know both at the same time. So right now you know the mass because it's in a mass eigenstate means that you know the mass to 100%. So if you know the mass to 100%, then you don't know the flavor to 100%. Meaning that when you have a muon anti-neutrino coming in, which should not interact with an electron because those are different generators, right? This is not an analog vertex. This can kind of change, mixing is the word they call it, or oscillation, to an anti-electron neutrino, and thus form a W to form other stuff. Or actually, the way it actually happens is going this way, but either way, right? So the point is that an interaction which is normally forbidden because muon anti-neutrino and electrons do not mix is allowed. Actually, this is not the right one. Yeah, this is the one. Is allowed when because you are in a mass-eyed state, and thus the flavor is uncertain, and because there's a possibility of doing this. It turns out that possibility is not even that bad. It's much larger than with the CKM matrix. There's an equivalent matrix for neutrinos that has some name or other that governs this effect, which is called neutrino mixing or neutrino oscillation. And there's the subject of most neutrino experiments going on. You guys saw the big neutrino control room at Fermilab, right? For Dune and Minerva and something else, Microboon. Those are all looking at neutrino oscillations. Because what happens is the probability of this happening changes with distance that the neutrino travels. And so that's why they have to do different lengths. So that's why they have some locally and some in Minnesota and then another one in South Dakota, because those give them different bits of information to measure this effect. So this is neutrino oscillation, but this is actually the only Feynman diagram you needed to draw. And here you put anything you want, right? If you want to do that. I didn't even say it had to be stable, so it doesn't be anything. Okay. So that was that one. Yeah. Ions are not stable. Like I said, in this one I didn't specify, so you could have put whatever. In real life, this one also would go to a pion, which would then indicate as something else. Pions are very common products, but you would need to know that. All right, number two. Number two is a new one. I wanted to see how it went. I guess it went about how I thought it might. It was pretty tricky because it says, look, the first thing it says is the probability of measuring SC to be spin up, right, which basically means this is 1/3. And therefore measuring down is 2/3. And so from this, you should be like, oh, I can do this, and you can write something like, you would write something like this, right? Right, you would write something like this, right? This gives you 1/3 chance of getting up, 2/3 chance of getting down, and everything's good. Except for the fact that then it says the probability of measuring SX, the h bar over 2, is 5/6. So in other words, the probability of this has to equal 5/6. If you take this and try and calculate it on this, you get something with root 5 in it or something like that, right? Or is that this one? Right? You get something that is not 5/6 because 20 square roots in it. Okay? So this clearly is not going to work because while it fits the first one fine, it does not fit the second one. And a lot of people got stuck there, and I was looking for people who would have the key insights to get around this. And the key insight is kind of an old one. That's why I thought some people might have gotten it. But a few people didn't. And I think one person, maybe even two, got all the way. Maybe it was just one. Anyway, so like it was possible, but a few people got the crucial insight, which is to get these both to work, you can't do it like this, right? There's only other way to do it, which is complex numbers. You need to use an imaginary number, and primarily that's what I was looking for. Was did you realize you need to use an imaginary number? Figuring out what to do from there can be tricky if you're not sure what to do, so I was just looking for evidence of complex numbers in there. You have to realize that it's not so much that this has to be 1 and this has to be 2, but what has to be true is you have to have something that looks like this, right? You know the wave function is going to look like this. And let's make it a little bit easier, factoring out 1 over root 2. Then we know that a squared has to equal 1, and b squared has to equal -1. What am I talking about? B squared has to equal 2. That's right. Right? That part we know. Then we also know, though, that when we combine it with, when we take this step and combine it with this, then you end up with, say, there's So one factor of 1/3 here. And if you combine these together, and then another 1 over root 2, so that could be 1/6. I'm shortcut you some of the math. But you're going to get that, yeah. Sorry. You end up with this, right? Okay, if you put that in there, this is what you'll get, which is to say that the a plus b quantity squared has to equal 5, which again is doable if it's a complex number, right? In particular, at this point you can start to work it out, and the way you want to work it out, if you want to do it, is just let a equal 1, because that works, and then figure out, and then let b equal some other, c plus I d. Right? So a real and complex part, and then plug that into here, and you would get 1 plus c squared plus d squared equals 5. And then if you plug that into here, you would get, this is absolute value squared, you get c squared plus d squared equals 2. And then by combining it, you can work it out. Or you can actually kind of do it by just inspection. You guys can check that with easy numbers. The number that works easily is 1 plus I. Squaring that gives you 1 plus 1, which is 2. But when you put it into here, it gives you 5. Because you get 2 plus I, which squares to 4 plus 1, which is 5. Okay, 1 minus I also works just as well. So the overall wave function, technically there are a few others, but by far the easiest way of writing it is like this. This actually is plus or minus, either one works. Okay. So that was a tricky one, especially that last part of the algebra, which is why I was focusing and grading on seeing if people realize you need that imaginary number. Keep on forgetting those imaginary numbers, Like I've used that trick like 3 times on you now. It always works. So anyway, that was the trick to that one, or the key to that one, I should say. It's not a trick. All right. On the other hand, question 3 went well in general. That's good. There's a big Stern-Gerlach thing, and the key is a few people didn't read what it said at the top about how these things split. They don't split evenly to 1/3. Right, 0 is 1/2, and the others are 1/4. A few people missed that. In this, and just do it simplified here. So you're going to have, 1/4 here, 1/2 here, and 1/4 here. These split yet again, so you get 1/16 here coming through, and 1/16 coming through. Wow. Not 1/6, this is 1/8 coming through. Because you're measuring something perpendicular, right? So you just resplit, take 1/4 and then multiply by 1/4 to get 1/16. Here, however, since you're measuring z again, this is still 1/4 because the z was negative before, it's still negative now. Then you bring those all back into another z box. But all of these are going to go here because you still are measuring, for these guys, you're measuring z 3 times in a row. Therefore, these all stay here and they all get absorbed by the bumper. So the only ones that matter are these guys. You have a 1/16 plus 1/8 going in, which I know this is hard for some people, but that gives you 3/16. And then 1/2 of those gets through, so you should get 3/32. Overall, people did well on this. If you didn't get the answer, you often got close to it. All right, then I asked, what happens if they're all commuting? If they're all commuting, what changes? Well, what changes is that measurement of x has no impact on the measurement of z, right? That's what commuting means, that you can know them both at the same time. And so it means that whatever you measured here is the same thing you will measure here. It will not reset this time. And so for part B, you would have, once again, 1/4, 1/2, 1/4. and that was split out to these guys, which would just as before cut you to 1/16 and 1/8. Sorry. But now when you go back into here, the top half would go straight through to here because of their commute, that if they were plus z here, they would still be plus z here. If they're minus z here, they would still be minus z here. So these guys go through. So the only one that goes through would be the ones from the middle, and that would be 1/8. All of them would go through. You get 1/8 there. And then part C was really too easy for this test. But anyway, because I just asked you to find it right there, and the answer is that you would get 1/2. Yeah, 1/2. Negative plus 1/√2, 0 plus 1/2 positive. Or a few minor variations on that. And I even forgave you if you wrote √4 as like 2. All right, number 4. Number 4 was kind of up and down. I would have liked to see better scores than number 4. I mean, of course, I'd like to see better scores overall, but like on this one, I thought we could have done better in the class. Some people did fine, some things. The key is remembering how the double slit experiment works, right? The reason an interference pattern doesn't appear is because we make a measurement. This interference pattern doesn't appear when we make a measurement of which slit it went through. And I mentioned to you that it was not about that it was whether it was possible to figure out which slit it went through, not about whether you look at it, right? So the question is, in which of these situations is it possible to figure out which slit it went through? And the answer is this one. In this configuration, these all have spin down, these all have spin up. That doesn't mean they won't interfere. They'll still interfere just fine. But it is now possible for me to distinguish between the two, right? That fact that I can distinguish between them means that the wave function has collapsed, because this measurement now distinguishes which one went where, and now you have no interference pattern. Okay, so the key was to remember how the actual double slit experiment worked in the first place. And when I was looking for, I was focusing on the explanation. What I was looking for in the explanation was we have to talk about being able to know which slit it went through, right? That's the key. If you knew which one it went through, if they were distinguishable from each other, if I could look at an electron and know and make a measurement and know which slit it went through, then that would do it. All right. Now, how do you make it happen? I was glad to see most people got the basic idea of how to make the interference pattern reappear. Sometimes referred to as the quantum eraser. That's to say, because I mentioned this, I never explained it. I mentioned that it is possible to take a measurement of which slit it went through, and then delete that information, and then the interference pattern reappears. But you can't just delete it off the hard drive. You have to delete it like out of reality, And so the way to do that is to remove all the information of this measurement that took place, and we can do that by simply putting it through a perpendicular measurement, x or y. And then here's the part that then you have to get them identical after this, right? Now, if you measure it, there is no way to make a measurement to know which slit it went through because the z information has been destroyed and the x information is now identical. They're both positive in the x direction. Yeah.
Would it work if putting x numbers put on one and then put z after that and then
Some people put a z after it with then the same thing coming out, and that would work too. Yeah. It's just not necessary, right? This is sufficient. So this first one measures which slit it goes through, thus destroying the interference pattern, collapsing the wave function. This measurement in a perpendicular direction, right, now removes that old measurement, replacing with this new one, and thus erases the information of which slit it went through, thus recreating the interference pattern. It's something called the quantum eraser, and while the experiments that we've done have done with photons instead, which are easier to work with, in principle, this has been measured in the lab. Yes? If you used only one, I believe I gave a partial credit for that one because they have to go through separate things. Like you can't unite them because then there'll only be one selection at that point. So I should have given decent partial credit. Is that right? Okay. Yeah, actually saw it quite a few times. If you put them both into the same string, they're not going through this. They're not going through two slits anymore. They got to be separate streams, right? Otherwise, it doesn't make sense. Yeah.
And how would that typically work bringing them together without them altering?
That would be hard to do. A big experiment, a big device. Yeah, the fact is, if you run them through the same device, there would have to be some kind of alteration, and that would mess up. You would no longer have two slits. Hey, you're here. And I'm going to have to find some other recipes.
Bring the mails.
It's all right.
Why? Bringing the
I remember this fairly well. All right.
Yeah, the midterm.
Next one. Next one is the pentaform problem. Parts of the pentaform problem I'm fine. I asked what could the colors be, and they have to be something that looks like this. Or be anti-VGA. They have to come out to colorless combinations. There has to be an RG and a V, which will be colorless, and then a fork with a color with its anti-color, that will give you colorless. If you did that, that would be full credit. Part B, violates conservation of energy. Gotcha. So those of you who thought that Dr. Rock would never do that, like give you a Feynman diagram that actually doesn't work. Actually, not only did I get you, I got myself because I wrote this problem, I don't know, 6 or 7 years ago or something, and then I put it back in, and then I put it back in, and I was like, I remember this problem, this is a good problem. And this was, so I wrote it like 7 years ago, then like, I don't know, 3 years ago I gave it again, and like, I put it back in, and I'm like, oh, this is a good problem, so I didn't like look at it, because I remember we're fine. And then it was like, it violates conservation of energy, and I'm like, what? That can't be right, I must have miscalculated, and then I realized, no, I did that on purpose. So like, okay, now a lot of people question about baryon number. So, is the pentaform a baryon? Well, no, it's not. But what is it exactly, right? It's a pentaform. But remember that conservation of baryon number really, as I mentioned briefly, and as you can see from your Feynman diagram, it really comes down to conservation of quarks, right? The variant, because baryons have 3 quarks and antibaryons have 3 antiquarks. Maze has a quark and an antiquark, so they don't contribute anything, right? So conservation of baryon number is necessary because the number of quarks minus the number of antiquarks has to stay constant, right? And we see that in our diagrams, and I mentioned that briefly at some point. So you can say, well, wait a minute, this thing is basically a baryon and a meson, right? If you split it up, all the quark lines work fine, right? The number of quarks goes around. And so based on that, you should say this does not conserve baryon. This does not violate baryon number conservation. The baryons go fine. This counts as basically one baryon plus a meson, and everything works out fine. You could also remember that for the first 3 laws, not conservation of energy, but the other 3, if the Feynman diagram is drawable, that means it passes those laws, right? You can't draw a Feynman diagram that violates charge, lepton number, baryon number. So based on all those, I feel you should have been able to figure it out. If you put baryon number in violation, I just took out a small number of ones. So. All right, then we get to the statistics. For the record, I actually gave you the easier version of the one I originally had. I came up with one that's like, this one looks too hard. Let me give you the easier one. So the key is what is distinguishable and what is not. So if we begin with not including color, these 2 are potentially indistinguishable, and they are fermions. Because quarks are fermions. You should have gotten that. Quarks go into the big fermion heading on that particle list, so you should have gotten that one. And they're spin 1/2. Those are all things that are true. And you had them all in particles. So these are identical fermions, and these are identical fermions. And these 2, however, are not identical fermions, right? Because they have different flavors, so they're distinguishable. Right? They have different masses, different all sorts of things, right? This one, of course, being an antiquark and a different flavor, it's clearly distinguishable. So what you have are 2 pairs of distinguishable fermions, of indistinguishable fermions. right? But these are all distinguishable from each other. Similar to that level 3 problem we had. And so here's the thing. If they're fermions and they're spin 1/2 particles and they're identical, what does that mean? They can't have the same spin states then, right? Because that's the only other thing you have, is spin. So that means these have to be opposite spin. It could, of course, be the other order, but order doesn't matter because they're identical. And these also have to be opposite spin, which means the only spin, these both have to cancel out to 0 spin. The only spin that matters, therefore, is the spin of the anti-quark. And that one has a 50% chance of being up or down, and therefore the overall probability is 1/2. Yeah. Yeah. All right, so that one actually was a very straightforward problem once you identify what it's asking. Part D is not so straightforward. And disclosure, no one got that one. I think someone did last time I gave it, though. At least that's my recollection. I didn't actually. So let's talk about how to do it. Now you have to take color into account. So this one, like you basically have to put everything together because you basically have the colors that look like this, right? And if you didn't get A right, you're going to have trouble with D. Although actually most of the wrong variants on A would still work. So for the statistics, to be fair. So let's redo this again. The key is that there are different color combinations you can give to them. But you have to be very careful about doing it. So here's how I did it. I think probably the easiest way. First of all, remember, R, G, and B have no intrinsic knowledge. We've never seen a colored particle, right? So they're basically arbitrary. So there's going to be this kind of, they call it like combinatoric factor because R and B and G are all basically the same. They are interchangeable. It's a question of the combinations that matter. So what you can do to keep that under control is to pin it down by just saying the anti-quark is going to be R bar. It could be D bar or G bar, but that won't affect, that will like be a scaling factor that affects the numerator as well as the denominator. It won't make a difference. So like I said, let's call that R bar. So the remaining guys have to be R, G, B, and another R. Okay? So let's write out the combinations here. There's not as many as you might think. I can have, for example, R, G, B, R. That was good. I can have R, B, G, R. This one's different because it's an up quark that's blue and a down quark that's green, instead of an up quark green and a down quark blue. Right? I can have R, R, G, B. What? Yeah, you say, wait a minute, these have the same color. Yes, but they can have different spins, so it's possible, right? And I can do G, D, R, R. This is different because here it's the up quarks that are both red, here it's the down quarks that are both red, so that's distinguishable. And this is actually all the cases. You're like, wait, what about G? Oh no, remember, order doesn't matter when they're identical, right? So the order of these is not going to matter, nor the order of these. Not going to matter, right? So all of the combinations are just rearrangements of this order. So you can try the ones to discover these are the only ones that matter. Okay. As far as the calculations for these are going to give you the same answer because G and B are arbitrary. It's just counting. And these two will also give you the same answer because it's the same thing. It's just these, whether it's the ups or the downs you're looking at, right? But they're definitely different from each other. So let's look at this one here. Okay. For this one, you have, these are all distinguishable particles, right? And so you have, so you have a red, a green, a blue, a red, red up versus the red down are different from each other. So they all have a different flavor or a different color. Therefore, they're all distinguishable, 5 distinguishable particles. That means there are 32 combinations. You could write them all out, it wouldn't take that long. But you should know there's 32 combinations of each of these, because now they're all distinguishable. You use regular statistics, right? So you know there's 2 to the 5th different combinations, 32. As for how many of them give you a total overall spin of plus 1/2, then you can start looking at it like this. Well, to get plus 1/2, what do you need? You basically need 2 ups and 3 downs. 3 ups and 2 downs. 3 ups and 2 downs. So to do 3 ups and 2 downs, you can do it like this. Down, 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 up, up, up. And if you think about it, you only really have to keep track of the downs, right? Because the rest are all up. So So then you have down, 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 down. I'm doing it fast. It's actually not that hard. It's going to do it fast. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? 10 over 32, which is 5 over 16. We're not done. Because what about these? This will give you something different. Because here, these two are identical. Right? They have the same flavor and the same color, and they're fermions, which means they have to have opposite spin. They must have opposite spin. So this one, these spins are locked down for the first two. Now the other three are distinguishable from each other. Right? So now we have just out of 8, which is only 8, only 2 to the third, or 8 combinations left. And you have, and you want to get 2 ups, 1 down. So there's 3 different possibilities. I'm skipping some stuff. You could have written it out. Yeah.
Why is it 2 to the third when you have like 3
You have 1, 2, 3 left. These are locked down. The total has to be 0. So you have 3 to the 8. So you have 2 of them that give you 3 to the 8, 2 of them that give you 5 to 16, 5 over 16, right? Since they basically balance out, the easiest way to do it is actually to average the 2 probabilities, like so. You could have done it properly. It comes out to the same thing. The numerator there gives you 11 over 16 divided by 2 gives you 11 over 32.
Is that the final one?
Yes. Did you get that?
No.
Okay, just making sure. I should have tried.
So then, do you just not worry about all the possibilities about these bars?
These are identical.
No, yeah, I'm talking about you change.
Oh, right. So if you change the different possibilities for S bar, nothing else changes here, right? So basically you multiply your numerator and your denominator by 3. But you multiply the numerator and the denominator. So yeah, if you just put in G bar, then you'd be like, oh, it's all the same thing. And G bar would be all the same thing. And so you just repeat it over and over. The probability stays the same. Okay, that one was tricky. You should pay attention to that intent. So, sorry, maybe I should have told you beforehand. Let's talk about number 6. Number 6 was another one. I thought I graded it pretty easy, actually. If you just got the interference pattern, I gave you a 4, I think, which was, I thought, pretty generous, but maybe fair, because it's kind of an unusual problem, shall we say, right? This is a different kind of problem than we usually get, one I actually quite like myself, but one that requires creativity on your part to figure out what do we actually do, which is very much what physicists have to do, you know. And scientists of any sort, people, I mean, you know, it's problem solving. And so here's the thing. You have to measure the work function without a photoelectric effect box. That's tricky. So most people figured out that you could in fact take a laser and shine it through the 2 slits. Correct. And then you'll get an interference pattern here, from which you can measure delta y. And then you could use, and you could measure the rest with rulers, and you were allowed to assume that the lab had walls. And from that, you could, you would be able to calculate by using this is lambda L over D, and therefore since you could measure all these, you would know lambda, and then you can calculate the frequency using this equation. Now you have the frequency, and that's good. And then most people are like, good, now I know the frequency, and that's going to go into this equation. Oops, not H bar. Into this equation, and that's good. Except we don't actually know KD max. Then, a good number of you fell for the red herring I threw in. You know what a red herring is? A red herring is something that is an abstraction from the real thing. What was the distraction in here? No, the intensity. I let you vary the intensity of the laser. Does intensity have any effect on anything? No. It does not. That's the whole point of photoelectric effects, and it doesn't affect anything. So people are like, oh, you can change the intensity until something. No, changing the intensity does nothing to the photoelectric effect. right? At least as far as the work function is concerned. You could get out more electrons, but that wouldn't tell you anything. So what you have to do, and this was tricky and only a few people got the insight here, what you have to do is now you know the frequency of the laser. So now you put the metal here, shine the light at the metal, and what's going to come out? Electrons. And what do you do with the electrons? Put those through the double slit. If you put the electrons through the double slit and then put the cathode here, the cathode screen here, then you'll get an interference pattern. Right? Because electrons go through these, electrons interfere just as well as photons do. And therefore you will see it on the cathode screen, the interference pattern. From this interference pattern, from this delta Y, you'll be able to measure the wavelength of the electron. Then the wave of the electron is h over p, right? Which is momentum, right? Using the Broglie wavelength. And then from the Broglie wavelength, P equals mv. We're all non-relativistic to make it easier. A few people did put in relativistic calculations, and I let you go with that, but it's all non-relativistic here. They're not going that fast. So P equals mv, and kinetic, from that you get the velocity. Kinetic energy is 1/2 mv squared. That now goes into here.
Yeah, I asked you, if you really want to.
Correct.
You threw me off. You hit something instead of
You
that.
tried to read too much into me.
You sounded so upset with me. You're like, really?
You had figured out what he didn't want anyone to know how to
That's
get the
right,
correct
yeah.
answer on the test.
I usually respond that way in general because other people around you can hear your questions, so I don't want them to think you're right. So I usually respond to most questions with skepticism. I did that with Manny in the train problem.
Oh, yes.
I tell you that?
Yeah.
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 And I was like, oh, if you think so. And then he thought I was doing it wrong, and so then he made a completely wrong answer, and then made the right answer to begin with. Anyway. Okay, the last page went pretty well. With two noticeable exceptions, but they're not in this class.
What?
They thought it was a joke.
Two people, I have done this like every year for several years now. And this is the first time I've ever had two people have thought they should leave it blank. I should understand.
The way you said it was like, how people laugh, and you like laughing about like giving people a laugh.
Right, but the rest of you figured it out. Yeah. Oh, 6B, I'm sorry. Wow, thank you. 6B is one simple fact. There's really only one that works. I would have entertained other ones if you come up with one, but most of them were very implausible things. I gave partial credit as I thought was appropriate. But really the key, which is key in anything with a photoelectric effect, is that you have to have the right frequency of light to be able to get photoelectrons off in the first place. Right? If your light is too low a frequency, if it's below the cutoff frequency, then no electrons come off and nothing works. Right? That's true with anything to do with the photoelectric effect. That was a tricky one. It wasn't worth a lot of points, so I figured it was fair balance. Part A was actually worth a good chunk of points, but most people got most of them. A 4 is 15 points, and a 4 is 11 points. I think you got most of them. Yeah.
For 6B, it's going to be like.
My God, that's really.
I have pretty like.
Still what?
I said perception is reality.
Did you do that?
Heck, have it.
Did you put that down? I swear I remember that.
Which one was that?
Doppler effect that could allow you to adjust the frequency, and that's ridiculous.
16.
I made the assumption.
Already getting the electrons through the double slit is already a
Exactly.
laser at near speed to the speed of light is really way too far.
But I mean, it's correct.
Okay, number 6. Heisenberg uncertainty principle. Most people did well on this. I was glad to see that. The key is he measured one, he measured the other one, but that's not what the uncertainty principle says. It's because they don't commute. If you now, but what I really liked to see, I tried to grade it as fairly as I could. What I really liked to see was that that if you went and measured that position again, you would get something different. That's really what I wouldn't say that's necessary to get a 7. I graded as fairly as I could, but what I liked It's what I thought was the clearest argument is to say if you measure the position again, it would be just as precise, but it'd be a different answer, right? That's what I was supposed to looking for. For the lab practical, most people did well on that as well. They're entangled particles. To get the full credit, which was actually not super, most people got most of the credit, not a lot of people got full credit, because to get full credit, you needed to say that it was about spins. You didn't mention the word spin, that you didn't get full credit.
So all we had to do was just say the word spin.
That you needed to say something about the chocolate covering concealing it, or that you had to make a measurement of it.
I said spin, but I didn't understand.
It's okay.
Oh, I think I read this sentence. I can go change that. Remind me. It's like it's like a tenth of a point. Okay. So anyway, so that one went fine. I said with two notable exceptions. The last one? Yeah. So the colors, white and brown, the white chocolate and the dark chocolate, it's actually semi-sweet, correspond to two different spin states, up and down, whichever one you prefer to be up. And the fact that they're concealed with chocolate means you don't know in advance. It starts as one thing, but you break it into two. You can move them separately from each other. But if you measure one, which means bite into it and see what's in the center, you automatically know what is in the what is inside the other one without looking. You know what color is inside the other one. If you bite into this one and it's dark chocolate, you know the other one's white chocolate. Vice versa. So that's like the whole thing. Yeah. No, you did. So you had the basic. Thing. You just actually for yours because you talked about hadronization, which is not actually relevant. But a 5 remember, it's not 5 out of 7. A 5 is 85%. Yeah.
With these chocolate analogy, the boards,
Yes, actually, of course, it's really a hidden variable because I can't actually make entangled chocolate that way. Awesome as entangled chocolate would be. No, that's the thing. Entangled chocolate would not be awesome. It would still be either white or dark chocolate. It would not actually. But the white was too sweet. I finally got the texture right. It's hard to melt white chocolate, but it was too sweet. You know, a way to cut it or something.
No, it was amazing.
You really like it?
Yes.
Okay.
I actually thought it was too sweet.
Well, I think you're wrong.
Okay. Well, at any rate, and I saw there's some like chocolate spheres out there, and people were like, "Sorry about that." No, but I thought that was really a compliment. So.
You can detect the exact point where I opened the chocolate because you start seeing chocolate.
Oh, for the wave function, any wave function that was normalized, I gave 2 points for. If you missed normalization, I only gave 1 point. So yes. You did not have to put all I could say. You could have. I didn't say anything, but you could have. And if someone did that, someone just put say equals 8. Now you're sure you're confident. Like, all right. That is the correct way to do it. Okay, so let me get these back.
Na 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 na.
Oh, that's so neat.
What?
It's like roast meat. Let's see what's a good one.
Scroll. Oh my god, that's fucking never mind.
What?
She's like a YouTuber who's famous for being anorexic
Oh.
and super goth and
You
crazy.
said the distinction. How they distinguish? Oh well, I mean, obviously, what's obvious to one person, not obvious to everyone. Anyway, that was
Awful.
Oh,
Okay.
yeah, I got it.
Okay.
Of course I got it, it's me.
Avoid Sherbach.
I should have written I down.
That's not a really good road.
What must be alive, but then you work with the eyes on
Not bad.
What?
Oh, yeah.
What about her? How could you possibly? Oh, that's a little racist. That doesn't count. I don't count racist things as actual things because that's not personally attacking them. That's just attacking a general group.
What?
Do you not get it?
No.
Do you know what don't ask, don't tell is in the military?
No. Which is weird because both
Actually?
my were in the military.
Okay, so
Really not really.
hang on. Let me end this.